This lecture is part of a short online course on category theory and will be about limits and colimits in categories. So I'll start with a simple example of a limit, which is a product of two objects. So to be definite, let's look at topological spaces. So if you've got topological spaces x and y, you can form their product as a topological space, where you take the underlying sets of x and y and take their product, and then you have a topology on where the base of open sets for the topology on x and y consists of products u times v, where u is open in x and v is open in y. This is not acceptable in category theory because we're looking inside the objects x and y at their points and so on. And in category theory, you're not supposed to do this. You're supposed to just look at morphisms. So let's find a different definition of the product that doesn't look inside the spaces. So if you've got the product x and y, there are natural projection maps to x and y. And the product has the following universal properties. Suppose you've got any space Z with maps to x and y, then you can see that Z factorizes through the product in a unique way. It's fairly obvious how to write this down. And we're going to use this as the definition of the product of x and y. It's a sort of universal object mapping to x and y, in the sense that for any other object mapping to x and y, there's a unique map factoring through it. Well, the first problem you might notice is that this doesn't actually define the product uniquely, because there can be lots of different set topological spaces acting as the product. In fact, anything isomorphic to x times y will also be a product. Fortunately, the product is actually unique. So suppose I've got two products of x and y. Let's call them P1 and P2. That means they're both of maps to x and y, and they're both universal. Well, because P2 is universal, the map from P1 to x and y factors through P2, and because P1 is universal, we get a map going back the other way. And then the composition of these maps must be the identity, again because of the uniqueness of the map from P2 to x and y, factoring through P2. So products are unique up to isomorphism in any category, provided they exist. So if you look at products, you can take products of rings, sets, groups, topological spaces, and many other things, and you find the usual definition of products in all these categories has the following universal properties. So we've got a unique definition of the product that works for all these different cases. So let's have a look at some other examples. First of all, instead of taking a product of two objects, we can take a product of an infinite number of objects, x1, x2, x3, and so on. And again, this is an object x1 times x2 times x3, and now it has maps to all these xi's. And it's universal for maps to all these xi's. So if we've got any object S mapping to all these xi's, then it factors through the product in a unique way. And if you look at this for topological spaces, if the xi's are topological spaces, and you look at the definition of the product topology, it's not at first sight clear what the best thing to do is. You might take a basis of open sets to consist of all products like this, where the ui are open in xi, and that's not actually the right topology to put on the product. I mean, it gives you a topological space, but it's called the box topology, and it's not really a very nice one. The correct topology is one where all but a finite number of ui are equal to xi. And when you see this definition in a when you're learning topology, it seems to be a bit of a funny definition. It's not quite clear why you do this. I mean, it turns out to behave well. Well, category theory explains why. It's the topology that gives it this universal property. So category theory sort of explains why you choose that particular topology on the product. And of course, for all the other categories I mentioned, you can write down infinite products, and they turn out to be the usual ones. The next example of a limit is something called an equalizer. So an equalizer is as follows. Suppose you've got two objects A and B in a category and two morphisms to them. Then an equalizer is an object X mapping to A, which such that these two compositions are equal. So if I call these maps F, G and H, it would mean GF equals HF. And the equalizer is going to be a universal object with that sort of makes these two maps equal. In other words, if I've got a space S mapping to A such that these two compositions are equal, then there's a unique map from S to X, making this diagram commute. There's one example of an equalizer that you've come across rather often. So a special case is just kernels. So if A and B are abelian groups and F is a homomorphism from A to B, there's a second homomorphism which is just the zero map. And the equalizer of this is just the kernel of F, which you can see it makes these two maps equal, and it's kind of obvious that it has this universal property. So the next example of a type of limit are called pullbacks, or fibered products, or several other things here. It's a bit like a product, except X and Y both map to an object Z. And the product over Z, X times over Z, Y, is a universal object that maps to X and Y and makes this square commute. In other words, as usual, if there's any other object X mapping to S mapping to X and Y making this commute, then there's a unique map to X times over Z, Y. This appears a lot in algebraic geometry as a base change map. If you've got an algebraic variety over a field, say, you can change to some other field, or rather the spectrum of another field, and you get a new, I guess it'd be a scheme rather than a variety, a new scheme given by that. So another example of this is, suppose you take Y to be, say, the tangent space of a manifold. So it's all tangent vectors of all points, and this projects to the manifold M. And then we can take a point of the manifold M. Then the pullback of this will be the tangent space at this point P, as you can check fairly easily. You can describe the pullback explicitly for sets. Turns out to be the subset of X times Y of points X, Y with the same image in Z. And for most other categories, the pullback has a rather similar description. Another example of limits are inverse limits. And here's a rather famous example of an inverse limit. Let's take the p-adic numbers. Now, to take the p-adic numbers, you take the integers mod p and the integers mod p squared and the integers mod p cubed, and you kind of go on like that. And what you do is you take a p-adic number is given by picking an element from each of these groups in a way that's compatible with these restriction mappings. So the p-adic numbers Cp have maps to all these spaces, and these all these little triangles commute, and it's universal with this property. So if you've got any space S, any group S mapping to all of these objects, then it factors through the p-adic integers. And inverse limits in general are defined in a similar way, except instead of taking Z z modulo p to the n here, you would take some other object in some other category. Well, now that we've seen all these examples, we can give the general definition of a limit. So what we do is we just take a category C and we take a functor f from some category j to c. And what we're going to do is we're going to take the limit of an arbitrary functor, and I'm going to show you how all these other sorts of limits are just special cases of this. So we've got a category j, so j might have various objects and morphisms. Who knows what it looks like? Let's draw some bits of it. And a functor from j to c means you essentially you pick objects in C for each object of j. So we might have f of j1 maps to f of j2 and so on, where this is j1 and this is j2, and we might have various other maps like this all over the place. And what you want to do is to pick a universal object, let's call it little c, mapping to all of these, that makes all these triangles commute. So the whole diagram doesn't have to commute. I mean, this map doesn't have to be the same as that map, but all these, for any morphism of the category j, you get a morphism here, and that morphism has to commute with the two arrows from C. And of course, we add a universal property, so if you've got any map, any object S with maps to all of these making everything commute, there should be a unique map going like that. And just as for products, the limits are unique up to isomorphism if they exist. Limits don't necessarily exist. And the proof of this is just the same as the proof I sketched for the products being unique. And now we can list some special cases of this. So here's the category J, and then I'm going to say what the special sort of limit is. So first we could just take J to be 2 points. And then the limit will just be a product of two objects, because a morphism from a 2-point category to C is just two objects at C. So we just have X and Y, and we want X times Y mapping to both of these. Or J could be an infinite number of points, and this would give us infinite products. Or J could be this category here. We just take two objects and two morphisms between them, and then the limits are going to be the equalizers, because we've just got a map X and two maps to Y, and we want something mapping to X, making all these equal. Then we could take this category here. We just take the positive integers with a map from m to n whenever m is greater than or equal to n. As well as these morphisms I've drawn, we should also have composition morphisms, like one going from here to here and so on. And these correspond to inverse limits. And there's one more case that I didn't mention because it's frankly a bit boring. We could take G to be the empty category. Well, what happens here? Well, here you find the limit is a final object of your category. This means there's a unique map from X to, let's call the final object something, let's call it a blob. There'd be a unique map from X to blob for any object X. And if you unravel the definition of a functor from the empty category to a category, you will find that the limit of that is just a final object. So a final object for sets is just a set with a single point, and a final object for groups is just the trivial group, and so on. So final objects aren't really terribly interesting. Next, as well as defining limits, we can define colimits, which are just like limits, except you change the direction of all the arrows. So I'm not going to go through these in detail, but I'll just give a few examples. So if we've got a functor from fj to c, then what we do is we have fj1, we have all these elements, fj1 maps to fj2 and so on, whatever the category f looks like. And a colimit is going to be an object such that all these fj's map to the object, and of course all these little triangles should commute, and as usual it should be universal with this property. So if you've got any other object D with maps to this, then there should be a map from C to D, a unique map from C to D, making all these triangles commute. And let's just give some examples of colimits. And we will just run through the categories. So if your category J is 2 points, this is called the coproduct. And let's give some examples. For the category of groups, this would be an amalgamated product. No, not an amalgamated product, sorry, it's the free product of two groups. Group might be G star H, which is sort of the biggest possible group you can find that's generated by a subgroup G and a subgroup H. For commutative rings, the coproduct is just the tensor product of rings R1 tensor with R2. So you notice there are maps from R1 and R2 to the tensor product, and it's sort of universal with these properties. Then we can form infinite products or coproducts. The only thing I want to say about this is for abelian groups, you notice the coproduct is actually equal to the product. And this is actually quite unusual. For most categories, the coproduct has nothing to do with the product. But even for abelian groups, infinite coproducts are not equal to infinite products. So let's look at abelian groups. The infinite coproduct is sometimes called the direct sum. It's actually a subgroup of the product consisting of all elements of the product, such that almost all elements are zero. Next we can have, if you take your category J to be this one, which is the reverse of the one we had for pullbacks, these are called push-outs or various other things, and for groups you get the amalgamated product. So here, if we've got groups G and H with a common subgroup X, then the amalgamated product G star over X H is just the group generated by G and H that's as big as possible, except you identify the subgroup X of G with the subgroup X of H. And similarly for commutative rings, you have a tensor product R1 tensor over some other ring S with R2. So we have a tensor product of rings over a third ring. Next, if J is this category here, so in the case of limits this was an equalizer, here this is called a coequalizer. And an example of this is a quotient of abelian groups. So here what you do is you take two abelian groups A and B, and you take a homomorphism between them. Maybe A is a subgroup of B, doesn't really have to be, but then you take a second map 0 and you take the coequalizer of this, which means you're kind of mapping B to something such that you force these two morphisms from A to B to be the same. And you see the universal way of doing that is to take B over the image of A as a quotient group. So coequalizers are more or less the same as quotients, or sometimes called co-kernels. And if we take an infinite set of things like this, the corresponding colimit is sometimes called a direct limit. And a typical example is if you have some objects in, say, the category of sets or topological spaces. Suppose you've got an infinite chain of objects, each contained in the next, as sub-objects, then the direct limit would be a union. So unions of increasing chains are special cases of direct limits. Finally, if we take j to be the empty category, then the corresponding colimit is called an initial object. And an initial object, as you can guess, just has a unique morphism to any other element in the category. An example for sets, the initial object is just the empty set, which is not the same as the final object, which would be a one-point set. So next we can ask, what properties do limits and colimits have? Well, there's one very useful property, which is that right adjoints preserve limits. Now, you remember a right adjoint is quite often a forgetful functor. And left adjoints, as you can probably guess, preserve colimits. And left adjoints are often sort of free functors, although not always. So let's just see an example of this in action. So if we've got the map from sets to groups, we can take the free group on a set and we get a group, or we can take a functor going the other way where we just forget the group as a set and we get a forgetful functor back to groups. So we remember from the lecture on adjoints that this is a left adjoint to this functor here. So the fact that right adjoints preserve limits says that taking the forgetful functor should preserve limits. So a typical limit might be the union. So if we've got a product of groups and we take the underlying set of G1 and G2, this is just equal to the set underlying G1 times the set underlying G2. And this sort of explains why when you take the product of groups, you take the product of the underlying sets. If we try and look at coproducts, we notice that taking the underlying set doesn't preserve coproducts. For instance, the underlying set of the free product G1 of G1 and G2 has nothing to do with the set G1 union the set G2. I mean, these are just completely unrelated. So the forgetful functor preserves products and more generally limits, but certainly doesn't preserve coproducts. On the other hand, the free functor, if we take the free group on S1 union S2, that's the disjoint union, which is the coproduct, this is equal to the free group on S1, and then you take the free product of that with the free group on S2. On the other hand, the free group on S1 times S2 has absolutely nothing to do with the free group on S1 times the free group on S2. So taking the free group on a set preserves coproducts. It turns unions into free products, for example, but it certainly doesn't preserve products or other limits. So I'm not going to prove this. I'm going to leave it as an exercise. The proof is sort of fairly straightforward. Like most proofs in category theory, it consists mostly of just unraveling the definitions. The only difficult thing about it is trying to remember whether right adjoints preserve limits or colimits. And the only way I know to remember this is to think of an example. So you might think of sets and groups, and then if you think about it for a bit, you can sort of figure out that the forgetful functor preserves products but doesn't preserve coproducts. So that might help to remember which way around this goes if you've forgotten it. There's also a sort of converse to this, which is Freud's adjoint functor theorem, which says that if f preserves limits, then f often has a left adjoint. And often means we need some extra condition, which is, well, first of all, there are several different versions of this theorem giving various conditions. What all these conditions have in common is they're totally unmemorable. I can never remember what they are. This doesn't really matter because they're nearly always satisfied in practice. So if you've got a functor that preserves limits, there's a pretty good chance that it has a left adjoint. I should say this doesn't always hold. There's a notorious counterexample. The standard counterexample of this is free Boolean algebras. Not free Boolean algebras, complete Boolean algebras. So there's a map from complete Boolean algebras to sets, which is just the forgetful functor, and this doesn't have a left adjoint. It turns out there's no way to form the free complete Boolean algebra on a set. You can certainly form the free Boolean algebra on a set rather trivially, but completeness kind of mucks it up. It turns out there's no upper bound to the size of a complete Boolean algebra generated by a countable set. So although if it preserves limits, it nearly always has a left adjoint, but this isn't quite always true. And of course, if it preserves colimits, then it nearly always has a right adjoint. So let's see an example of using this. So we recall that a right exact functor in homological algebra says that if you've got an exact sequence of groups, so C is just the quotient of B by the image of A, then the functor has to turn this into an exact sequence, so half exact sequence of groups. And you notice that C is just the colimit of of this diagram here. In other words, it's the coequalizer. So if a functor preserves colimits, then it will so if a functor is a left adjoint, then we saw by the theorem above that it preserves colimits, so it's right exact. And what is very annoying and confusing is that left adjoints are right exact and right adjoints are left exact, and which is why I always have to stop and try and think about getting this the right way around. So let's see an application of this. Suppose we take the functor where f of some object is just the tensor product of this object with some fixed group y. What we want to do is to show this as right exact. In other words, if we have an exact sequence A goes to B goes to C goes to 0, then A tensor y goes to B tensor y goes to C tensor y goes to 0 is also exact. This is not exactly difficult to prove from the definition of tensor product, but is a little bit tricky. However, using this result from category theory, it becomes completely trivial, because what you notice is that the morphisms from X tensor Y to Z can be identified with the morphisms from X to the homomorphisms from Y to Z. So what this means is that tensoring with Y is left adjoint to take the functor taking hom from Y to something. And from this it just immediately follows that tensoring with Y is a left adjoint, so it preserves colimits, so it's right exact. So this gives a trivial proof of the fact that tensor products preserves right exactness. This is an example of the saying that one of the purposes of category theory is to make trivial results trivial. So this is an example of that. So finally, I'll just mention a slightly confusing problem. So suppose you take the integers and take a direct limit like this, where this is multiplication by 2. It's not very difficult to work out what the colimit of this is. It's more or less an increasing union of sets. So what it is a set of rationals of the form n over 2 to the m. However, you might think, well, all these copies of z are the same, so let's simplify it a bit and just identify them all and take the colimit of this diagram here. Well, the colimit of this is just 0. So what has gone wrong? Well, what's going wrong is this is not really a subcategory. You don't take colimits of subcategories. What you take colimits of are functors from something to the category. So in this particular case, we're taking a functor from this category to abelian groups, which if the images of all these are the same, it's not actually a subcategory. If you try and make it into a subcategory, you get the wrong colimit. If you're feeling rather confused by this example, you're not alone, because one of the world's most eminent mathematicians got into a complete muddle about it not so long ago. So it's one of these facts that's trivial but very confusing. So you don't take colimits or limits over subcategories, although you quite often pretend you do because those are easy to draw. You really take them over functors.